3i Atlas was never supposed to survive this. On October 25, 2025, the Sun unleashed something we hadn't witnessed in more than a decade. Not one, not two, but three massive coronal mass ejections erupted in sequence from the far side of the solar disk, each carrying billions of tons of magnetized plasma, ejected with the force of a planet-wide explosion. At first, it looked random, chaotic, just another burst of stellar weather. But then, the data aligned. All three ejections were moving along the same narrow corridor of space, their magnetic fronts folding into one another like overlapping shock waves, and that corridor wasn't empty. Cutting through it at nearly 60 kilometers per second was something not born of our Sun, an interstellar traveller, cold, ancient, and unbound. Its name, 3i Atlas. In that instant, the Sun and the stranger met. Three plasma waves, billions of tons each, converged on a body no larger than a mountain, and the result should have been obliteration. Every simulation said the same thing: deflection, fragmentation, vaporization. No object that small could endure three direct hits from the Sun's most violent expression of power. But when the light returned, when the solar interference cleared, the object was still there, still moving, still perfect. Its speed, course, and orientation remained untouched. The CMEs hadn't destroyed it, they had curved around it. For solar physicists, that moment was more than an anomaly. It was a violation, a quiet contradiction in the language of physics itself. Because in a universe built on motion, impact means change. And yet, here was an object that refused to move, silent, balanced, as if it had anticipated the storm and simply let it pass. This is the 3i Atlas channel, calm, focused, and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to enter the giveaway for our exclusive 3i Atlas hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. On the morning of October 25, 2025, three major solar observatories captured something rare and nearly unprecedented. It began quietly, as it always does, a faint bulge on the solar limb, then a rapid expansion. Plasma, billions of tons of it hurled into space. A coronal mass ejection, commonly known as a CME. At first, it seemed like a typical far-side eruption. Powerful, yes, but nothing that would affect Earth or its surrounding satellites. But then came the second, and then the third. Three full-scale CMEs, each from the same magnetic region on the Sun's far side, erupted within an 8-hour window. In solar physics, that timing alone is noteworthy. But what made this event extraordinary wasn't just the frequency or scale, it was the direction. Each CME, measured independently by coronagraphs aboard NASA's Stereo-A, ESA's solar orbiter, and the GOES-19 satellite, showed a consistent angular trajectory. These weren't random outbursts, they were tightly focused expulsions of plasma, ejected from a constrained magnetic region in the Sun's southern hemisphere, and all three appeared to be aimed along a narrow corridor through the inner solar system. Normally, CMEs expand as they travel, forming broad, bulbous clouds that interact chaotically with interplanetary magnetic fields. They ripple, distort, and dissipate. But these three were different. The early frames showed coherence, directionality, suggesting magnetic confinement. And when solar physicists ran preliminary models, a strange overlap emerged. Each of the three projected trajectories intersected the same small region of space, a region currently occupied by an object moving at 60 kilometers per second. 3i Atlas, an interstellar visitor on a hyperbolic course, only days past perihelion. This convergence was not subtle. When plotted across multiple datasets, the CME cones all intersected within less than half a degree of 3i Atlas's projected ephemeris. The statistical odds of such alignment are minuscule, not impossible, but rare. It raised an immediate question in the heliophysics community. Were we about to witness the first recorded direct hit of an interstellar object by multiple solar plasma events? By the time this question reached the public domain, the CMEs were already on their way. Travelling at velocities ranging from 800 to 1300 kilometers per second, The leading edges of each wavefront would pass the object's predicted position within 48 hours. In most cases, this type of exposure is catastrophic for fragile objects like comets. The force of even a single CME can compress a comet's coma, distort its trajectory, or, in extreme cases, cause fragmentation. Yet here, we had not one, but three. It's important to understand the mechanics at play. A CME is not merely light or radiation. It is a billion-ton wave of magnetized plasma, dense with charged particles carrying immense kinetic energy. When it strikes an object, especially one with low mass and loose surface cohesion, momentum is transferred. That transfer results in physical change, direction, speed, shape. And so, the expectation was simple. Something would happen to 3I Atlas. Maybe not full disintegration, but certainly a measurable deviation, a wobble, a flare, an asymmetry in its coma. Even the most conservative models forecasted a minor course shift, at least several hundred kilometers over a few days. But that's not what occurred. What followed defied every forecast. And as telescopes turned back to the region 2 days later, they didn't see a shattered fragment cloud. They didn't see a spinning debris field. They saw the same object, untouched, the same path, the same velocity, no signs of impact. 3 CMEs had passed through the same corridor of space, and 3I Atlas had passed through them, unchanged. In astrophysics, alignment is rarely clean. Space is chaotic, and the odds of perfect overlap between independent forces are vanishingly small. That's why what happened on October 25th caught the attention of so many researchers, not because of intensity, but because of geometry. The Sun released not one, but 3 full-scale coronal mass ejections from the same magnetic region. Each eruption was powerful, each was fast, but most notably, each followed nearly the same path. A narrow, forward-focused stream of plasma projected along a corridor through the inner solar system. That corridor was not random. It aligned almost perfectly with the trajectory of a known interstellar object, 3I Atlas. Let's break that down. CMEs are not lasers. They are massive bursts of charged solar plasma, ballooning outward in wide arcs. As they travel away from the Sun, their dispersion increases. By the time they reach the orbit of Mars, a typical CME can span over 60 degrees of angular width. In essence, they become giant, messy clouds. But these 3 weren't messy, not at all. Observational data from NASA's Stereo-A spacecraft, as well as from ESA's Solar Orbiter and GOES 19, showed that each CME followed a narrow angular cone, just a few degrees wide. More than that, the cones overlapped. All 3 had ejection vectors that traced the same corridor, an invisible lane through space no more than a few million kilometers wide, yet stretching from the Sun's far hemisphere into the inner solar system. That lane, when projected forward, intersected with the exact ephemeris of 3I Atlas to within half a degree. Half a degree. In interplanetary scale, that's not a coincidence, that's a bullseye. Even more striking was the timing. The CMEs weren't evenly spaced over days. They emerged within 8 hours of each other, as if the Sun had pulsed 3 times, each wave following the last, all directed at the same volume of space. The magnetic region responsible for the eruptions had been quietly rotating out of view in the preceding days, slipping beyond the horizon as seen from Earth. It was located in the far southern hemisphere of the Sun, beyond direct observation by ground-based telescopes. Only spacecraft like Stereo and Solar Orbiter had visual access. When their data was compiled, the pattern became unmistakable. 3 CMEs, 1 source, 1 trajectory, and 1 target, an object hurtling at 60 kilometers per second through that very corridor. Some solar physicists began calling it the convergence zone. Others were more cautious. The Sun is unpredictable. CMEs can align by chance. But in internal briefings, the phrase repeated over and over, too precise. To understand why this alignment is so rare, consider how interstellar objects move. 3I Atlas is not bound to the Sun. It isn't looping in an orbit like a planet or comet. It entered the solar system on a hyperbolic path, one time only. No return. It slices through space in a single arc. For that arc to intersect so closely with 3 solar eruptions, none of which originated from Earth's side of the Sun, is improbable. Not impossible, but improbable enough to question whether geometry alone explains it. And so a new question formed. Was the alignment a coincidence, or was it reactive? Could the presence of 3I Atlas, its coma, its outgassing, its magnetic interactions, have influenced the solar surface itself? That idea borders on controversial, but in plasma physics feedback loops exist. Charged bodies can perturb field lines, and the solar corona is not immune to subtle electromagnetic interference. If the object was influencing its environment, shaping the very magnetic loops that later erupted, it would mean 3I Atlas wasn't just a passive traveller, it was part of the cause. Either way, the alignment stood, a corridor too precise, a pattern too focused, and a question that would echo through every chapter that followed. How did 3 eruptions, born in the chaos of the Sun, find their way to the same point in space? And what does it mean that something was already there? From the moment 3I Atlas was first tracked, one detail stood out above all others: its motion. It wasn't looping, curving, or cycling like the familiar comets and asteroids that orbit our Sun. It was slicing, clean, fast, and most importantly, hyperbolic. This object wasn't from here. When astronomers first plotted its path, they found something unmistakable: an orbital eccentricity of 6.1. To understand the gravity of that number, literally and figuratively, you have to understand how trajectories in our solar system are classified. A perfect circle has an eccentricity of 0. A standard elliptical orbit, like Earth's, hovers just above that, around 0.017. Comets with longer orbits can stretch into eccentricities of 0.9 or even higher, but they still return. They're still bound to the Sun's gravitational well. A value above 1 means something else entirely. It means escape. It means the object has too much velocity to remain captured. And a value like 6.1, that means it's moving so fast and so freely that it never belonged here in the first place. This is what defines 3I Atlas as interstellar. The object was first detected in mid-2025 by wide-field survey telescopes scanning near the ecliptic. Its motion didn't match the known background of asteroids. Instead, it was deviating rapidly across the sky, showing parallax shifts inconsistent with solar-bound objects. As follow-up observations poured in, from observatories in Hawaii, Chile, Spain, and eventually space-based instruments, its velocity was refined, just under 60 kilometers per second, relative to the Sun's rest frame. That number is crucial. It exceeds the solar system's escape velocity at that distance, which means even if all other forces vanished, it would still keep moving, outward, forever. But what's even more compelling than its speed is its precision. When interstellar objects enter our solar system, they tend to arrive on paths that intersect loosely with the inner planets, often at high inclinations or skewed angles. But 3I Atlas entered near the ecliptic, our solar system's main street, and passed close enough to Mars to be triangulated by orbiters. This allowed researchers to lock in its ephemeris, the predicted map of its motion, with extraordinary accuracy. That precision mattered more than anyone knew at the time. Why? Because it gave us a control point, a foundation of certainty against which everything that happened next could be measured. As the object approached the Sun, this trajectory became the baseline, and when the solar eruptions arrived, 3 CMEs in close succession, it allowed physicists to test a question that had never before been answerable. What happens when an interstellar object is struck by solar plasma? The expectation was simple: any force applied to a body in motion should alter that motion. It's basic Newtonian physics, and CMEs are not soft gusts. They're high-mass, high-velocity storms of charged particles. But after the storm passed, the trajectory of 3I Atlas hadn't changed, not even slightly. It was still following the same outbound arc, still accelerating away from the Sun with the exact same vector and velocity that had been forecasted weeks earlier. This is where things started to fracture, not in the object itself, but in the models used to predict impact behaviour. Because if the ephemeris held after the CME barrage, either the object wasn't hit, or something prevented the energy transfer from affecting its motion. The interstellar nature of 3I Atlas is more than a curiosity. It's the critical lens through which the anomaly must be viewed. This isn't just a comet behaving strangely. It's an unbound mass moving through our system without tether or history. A visitor, a probe, a relic. And what makes that trajectory so important is that it never lied. The math held true before the impact, and, inexplicably, after. A solar system object might have explained it away. But 3i Atlas isn't from here, and that changes the question from, why didn't it move? To something far bigger. How did it pass through our sun's fury, completely untouched? Before the CMEs struck, before the plasma wavefronts curved or scattered or disappeared into solar silence, there were models, dozens of them, built by heliophysicists, orbital dynamicists, and plasma theorists. All based on one unshakable truth: force equals change. In a system governed by Newtonian physics, when a moving object is hit by a high-energy wave, especially one carrying mass, something always happens. That something might be subtle, it might take days to detect, but it's measurable, it always leaves a fingerprint. That's what should have happened to 3i Atlas. At the time of impact, the object was already known to be moving at nearly 60 km per second, following a hyperbolic escape trajectory, eccentricity 6.1, through the inner solar system. It was small, estimated to be around 2.8 km wide, with a low albedo surface and a relatively thin but active carbon dioxide coma. 3 coronal mass ejections, launched within 8 hours of each other, had intersected the precise corridor of space that 3i Atlas was moving through, and each of these CMEs was massive. Solar ejecta travelling at 800 to 1300 km per second, with projected masses of over 1 billion tons per event. When modelled, even a 1% momentum transfer from these plasma clouds to the object should have caused a measurable deflection. We're not talking about explosive destruction, we're talking about basic orbital adjustment, a tiny drift, a few meters per second in delta V, that's all. But that tiny shift would accumulate. Over the course of a day, a 2 meter per second deviation becomes a 170 kilometer change in position. In 3 days, that becomes over 500 kilometers, and with the precision of modern instrumentation, ground-based telescopes, coronagraphs, Mars orbiters, and deep space tracking arrays, a deviation of even 10 kilometers would have triggered immediate red flags. Instead, when the object re-emerged after the final CME had passed, it was exactly where the pre-impact ephemeris predicted it would be. So what went wrong? If the models failed, it wasn't due to faulty calculations. The laws of motion haven't changed. The assumptions were simple. The object is small. The object is light. The CMEs are massive. The plasma is fast. A hit equals a change. All 5 of those statements should have produced a deflection. So physicists began double-checking each assumption. Maybe the mass estimate was wrong. That would make the object harder to push. Maybe the CMEs missed. But solar magnetograms and heliospheric imaging contradicted that. Maybe the coma absorbed the force like a sponge. But that would still lead to shock waves, disruption, asymmetry, none of which were observed. Instead, the coma remained stable, the trajectory remained stable, and perhaps most unsettling of all, the environment changed, not the object. CME fronts curved, plasma lines bent, but 3i Atlas held steady. And that's not supposed to happen. Even comets that survive perihelion, like Comet Lovejoy in 2011, show signs of struggle. Their tails bend, their comas flare, their trajectories shift under solar influence. And those are solar system objects with known densities and predictable compositions. 3i Atlas is an interstellar body, a traveller from far beyond our star system. That makes it even more fragile, more susceptible to solar violence. Or so we thought. Because what should have happened didn't. Instead of a visible reaction, we got a puzzle, a still frame in motion, a moment where the models failed not because the inputs were wrong, but because the outcome didn't follow the script. That silence of movement, of force, of resistance is what transformed 3i Atlas from just another interstellar visitor into a cosmic anomaly. The storm arrived. The physics was sound, but the object refused to play along. After the final CME cleared the observation window, telescopes across Earth and Mars turned back toward the region where 3i Atlas was expected to reappear. The anticipation was subtle, but real. Scientists weren't expecting devastation. They weren't expecting fireworks. They were expecting evidence of interaction, a deviation, a difference. What they found was neither. The object had returned exactly where the ephemeris had predicted. Not approximately, not within margin. Exactly. Frame by frame, coronagraphs and deep sky tracking stations locked onto the coordinates. Each comparison with pre-impact data returned the same result. No shift, no drift, no acceleration. The path of 3I Atlas was unchanged. This might seem like a minor detail to the casual observer, but to astrophysicists it was staggering, because that path, the outbound vector plotted weeks earlier, was expected to fail. Let's be precise. An object moving at nearly 60 km per second just past perihelion had been struck by 3 high-mass solar plasma waves. The combined force, even if lightly coupled, should have altered its trajectory by hundreds of kilometers over a few days. But nothing changed, not the position, not the velocity, not even the orientation of the coma. It was still following the hyperbolic arc mapped before the CMEs, with an eccentricity of 6.1, an unbound interstellar trajectory. The angle of escape relative to the ecliptic, the inclination, the heliocentric speed, every parameter matched the original model. And that shouldn't be possible. Here's why. The ephemeris is a forecast. It's a mathematical projection of where an object should be based on known gravitational forces and initial motion. But it assumes a closed system, no new forces acting on the object. Once the CMEs erupted, that assumption collapsed. Any interaction with those ejections, any transfer of momentum, would invalidate the pre-impact model. The object would shift, the ephemeris would diverge, and the observational data would reveal it. But that's not what happened. Across instruments, from NASA's Stereo A to ground-based radar in Chile and Hawaii, the reappearance of 3I Atlas was pixel perfect. Its brightness curve remained steady. Its coma showed no signs of lateral movement. The object had passed through 3 solar eruptions and emerged with no measurable change. And that's more than strange. It breaks the chain of expectations in orbital dynamics. According to Newton's second law, any net force applied to a mass results in acceleration. It doesn't matter whether that force comes from collision, radiation, or magnetic pressure. If something hits you in space, you move. 3I Atlas didn't. It's not that it resisted the change. It simply never registered the hit. This raised 2 immediate questions in the heliophysics community. First, was the object impacted at all? Second, if it was, why didn't it respond? To answer the first, scientists reviewed magnetogram data and CME vector modelling. The alignment between the 3 ejections and 3I Atlas was too precise to dismiss. The object's corridor intersected with the CME wavefronts for tens of millions of kilometres. It would be statistically unreasonable to suggest all 3 missed. That leads to the second question. Why didn't 3I Atlas move? Theories followed. Perhaps the object was denser than estimated. Perhaps it was shielded electromagnetically. Perhaps the energy of the plasma was deflected or absorbed by the coma in a way we've never observed. Whatever the explanation, one fact remains undebatable. The path held. And that, more than the CMEs, more than the wake, more than the chemical anomalies, may be the most unsettling aspect of this encounter. Because in science, when models fail and motion doesn't match force, the problem isn't with the universe. The problem is with what we thought we understood. In the physics of motion, momentum is sacred. It's conserved. It's predictable. And when it's transferred, especially in the vacuum of space, its effects are measurable. That's what makes the behaviour of 3I Atlas after the CME barrage so deeply perplexing. Because everything about this event suggested that momentum should have been transferred, but none was. To understand why that matters, consider what a coronal mass ejection is: a vast eruption of charged particles, mostly protons and electrons, ejected from the solar corona at velocities exceeding 1,000 km per second. Each CME carries mass, and when combined with velocity, that means momentum, an enormous amount of it. These aren't beams of light. They're physical flows of magnetized plasma with enough energy to distort satellite orbits, trigger auroras, and strip atmospheres from planets. Now, imagine 3 of these eruptions, each measured at billions of tons, converging on a single point in space. That point, the known trajectory of 3I Atlas, a small interstellar object with an estimated mass of roughly 5 trillion kilograms based on coma brightness and reflectivity. Basic physics tells us that if even a fraction of a percent of the CME momentum impacted the object, it would cause a detectable change. The math isn't complex. Assume a CME with 1 trillion kilograms of plasma travelling at 1,000 kilometers per second. That's 1 quadrillion newton-seconds of momentum. If just 1% of that mass encountered the comet, about 10 billion kilograms, and transferred its momentum efficiently, it would deliver a force equivalent to a 10 trillion newton-second impulse. Apply that to a 5 trillion kilogram object, and the result is a velocity change of 2 meters per second. Small on human scales, but in orbital. Mechanics, that's massive. Over just 24 hours, a 2-mess deflection compounds into a position shift of over 170 kilometers. Within 3 days, over 500 kilometers. Modern instrumentation, radio tracking, coronagraphs, deep sky imaging, can detect deviations far smaller than that. In fact, they can detect positional drift of just a few kilometers when tracking interplanetary bodies. But when scientists pointed their instruments at 3I Atlas after the CME window cleared, they found nothing. No shift, no lag, no lateral wobble, no residual spin. It was in the exact location predicted by its pre-impact ephemeris. Which leads us to a physics contradiction. If the object was hit, there should have been momentum transfer. If momentum was transferred, there should have been motion. But the motion never came, so either the object wasn't hit at all, it absorbed the force without responding, or the force was somehow deflected, without classical impact. Each explanation introduces problems. The first, missed impact, requires us to dismiss highly coordinated CME vectors that aligned with the object's path across tens of millions of kilometers. Statistically unlikely. The second, perfect absorption, would imply a material composition or structure capable of distributing force internally with zero external motion. That's theoretically possible in tightly bound, high-density objects, but 3I Atlas doesn't appear to be one. The third, momentum redirection without contact, ventures into exotic territory, electromagnetic shielding, ionized plasma interactions, or coherent field generation around the object. And while unusual, this idea is not science fiction. Plasma can behave in ways that absorb or redirect energy without direct contact, especially if structured magnetic fields are involved. Still, the mystery remains. The momentum is missing. The CMEs came and went, the solar storm passed, and the object stayed silent, not resisting force, but showing no evidence that force ever existed. For physicists, this isn't just unusual, it's foundational, because momentum transfer is one of the cornerstones of classical mechanics. When that cornerstone fails, not because the math is wrong, but because reality didn't follow it, we're forced to confront something much harder, that our understanding of how force behaves in space may be incomplete. When a small object resists a large force, the most immediate explanation is mass. Heavier objects require more energy to move. In physics, this relationship is simple. Force equals mass times acceleration. If you apply the same force to two bodies, the heavier one moves less. So when 3I Atlas didn't move after being struck by 3 consecutive CMEs, many researchers turned to a logical assumption. Perhaps the object is much denser than we thought. But this assumption, while reasonable, quickly ran into complications. Let's start with the baseline estimate. Based on observations from the Hubble Space Telescope, 3I Atlas appeared to have a nucleus roughly 2.8 kilometers in diameter. Its brightness, albedo, and coma behavior were all consistent with a small dark comet. From these parameters, and assuming a typical cometary density of 0.5 to 0.6 grams per cubic centimeter, its total mass was estimated at around 5 trillion kilograms. That mass is modest. Not tiny, but light enough that momentum from even a glancing CME should have caused visible change. So what if that estimate was wrong? To test that, researchers explored scenarios in which 3I Atlas was composed not of loose, icy dust, but of something far more solid: rock, metal, or even high-density mineral composites. For example, a nickel-iron object with the same size could have a density of 7 to 8 grams per cubic centimeter, more than 10 times higher. That would put its mass closer to 70 trillion kilograms. Suddenly, a CME's momentum might barely register. That model could explain the observed stability. But then came the contradiction. Optics. Objects that dense and metallic tend to reflect more light. They have higher albedo, and their surfaces respond differently to solar radiation. Yet 3I Atlas was dim, with a coma composition dominated by carbon dioxide, and only faint visual signatures, nothing like a polished metallic asteroid. In fact, the object was less reflective than average comets. That suggests not a metal-rich surface, but a dark, carbon-heavy crust, more like soot than steel. Then came the second issue, outgassing. Comets with dense, rocky interiors tend to show less volatile activity. Their surfaces don't sublimate easily, but 3I Atlas was active, even near perihelion. It was emitting CO2 steadily, an indicator of internal heating and volatile pressure. This points back to a low-density structure. You can't easily vent gas through solid iron. You need pores, fractures, subsurface channels, in other words, low cohesion, the very trait that should have made the object susceptible to impact, but didn't. Another hypothesis emerged. What if the object was larger than we thought? Brightness alone doesn't reveal size directly. If the nucleus were surrounded by a dense, non-reflective dust shell, too dark to be seen, too diffuse to scatter light, the optical measurements would underestimate its true diameter. Double the width, and you octuple the mass. A 5-kilometre wide body of the same density suddenly becomes a different animal, one with the inertial resistance to shrug off a CME. Or consider this. What if the object isn't spherical at all? Many small bodies in space are irregular, elongated, binary or lumpy. If 3I Atlas were tumbling, or if its shape caused light curve anomalies, the mass estimates based on reflected brightness could be off by a factor of 2 or more. But here's the twist. We didn't see signs of tumbling. Its light curve remained smooth, its coma stayed symmetrical. That would require not just mass, but rotational, stability, another trait unusual for something that should be getting buffeted by solar wind. So we arrive at a paradox. Every line of evidence that suggests density is countered by data that suggests fragility. It behaves heavy, but it looks light. It emits like a porous body, but moves like a metal one, which leads to an uncomfortable conclusion. Either our mass estimates are deeply flawed, or we're dealing with a body that resists force through mechanisms other than mass, something electromagnetic, structural, or still entirely unknown. In the aftermath of the triple CME event, analysts expected to see turbulence, chaos in the plasma trails, irregular field lines, maybe even a shockwave imprint on the heliospheric current sheet. Instead, they saw something else, something cleaner, something too clean. Across multiple solar observatories, NASA's Stereo-A, ESA's Solar Orbiter, the GUSS satellites, and the SOHO-LASCO coronagraphs, plasma wavefronts were captured in motion, erupting from the Sun's southern hemisphere and expanding into space. These coronal mass ejections were massive, high-velocity, magnetized clouds of plasma shaped by the twisted solar magnetic field lines from which they were born. Normally, when CME wavefronts expand, they bulge outward unevenly. They stretch, shear, and fracture under the influence of magnetic turbulence and background solar wind variation. But this time, the shape held. Each of the 3 CMEs launched on October 25th exhibited a narrow, coherent forward structure, remaining remarkably symmetrical as they approached the trajectory corridor of 3I Atlas. And then, the strangest thing of all occurred. The wavefronts curved, not around the Sun's magnetic poles or planetary magnetospheres, but around a small interstellar object. Captured in frame-by-frame analysis across multiple wavelengths, the CME fronts didn't impact 3I Atlas directly. Instead, they bent. Not chaotically, not with violent dispersion, but with a smooth, coherent curvature, almost as if redirected by an invisible shield. To heliophysicists, this wasn't a visual artifact, it was a magnetic anomaly. CMEs carry embedded magnetic fields. These fields can interact with other magnetic domains, whether natural or induced. When a CME encounters a planet like Earth, the embedded field of the CME can compress our magnetosphere, triggering geomagnetic storms. The same is true for Mars to a lesser extent, and even for small bodies with thin ionospheres. But 3I Atlas doesn't have a known magnetosphere. It doesn't have an intrinsic dynamo like a planet or moon. It's only a few kilometers wide. So how then did it manage to bend high-speed solar plasma? To answer that, researchers turned to the object's coma. The coma of 3I Atlas, as established by spectral readings, is dominated by ionized carbon dioxide, a volatile gas that, when stripped of electrons, becomes an active plasma environment. If that ionized gas carries electric current, due to outgassing, solar irradiation, or local charge separation, it could generate transient magnetic fields. Those fields might not be strong, but in plasma physics, structure matters more than strength. A small but well-organized magnetic field can redirect a larger incoming plasma wave if the field is coherent enough, and that's what appears to have happened. The curvature wasn't random, it was clean, predictable, reproducible across instruments. The CME arcs didn't scatter off into turbulent eddies. They formed a symmetrical envelope around the object, similar to what is seen when the solar wind interacts with planetary bow shocks. The effect was subtle, but undeniable. Instead of a direct collision, the CME wavefronts refracted, changing direction slightly as they passed the object, as if moving along a curved lens. Some researchers described it as a magnetic shadow. Others compared it to the hydrodynamic bow wave of a submarine, sharp, tight, and directionally consistent. But here, the medium wasn't water, it was solar plasma, and the object wasn't even a planet. It was something smaller and much more mysterious. Could a tiny body just kilometers across be shaping space around it? The math says yes, if the magnetic Reynolds number is high enough. That number defines how well a magnetic field is frozen into plasma. And for ionized CO2 moving at high speed through the heliosphere, that threshold might be met. The result? A field-induced plasma curvature, passive shielding, natural deflection. In short, the CMEs may not have missed. They may have been diverted, not by technology, but by physics. And the curve they followed? It was perfect. One day before the triple CME event, October 24, 2025, something subtle appeared in the background data of several solar observatories. At first it went unnoticed. It wasn't bright. It wasn't explosive. It didn't resemble the typical signatures of solar storms or cometary outbursts. It was a line, thin, faint, almost thread-like, trailing behind 3I Atlas as it cut through the inner solar system at 60 kilometers per second. But this wasn't a dust tail or gas filament. It wasn't even a typical ion tail shaped by solar wind pressure. This was something different. What multiple instruments had captured, independently and across different wavelengths, was a plasma wake. A structured, coherent disturbance embedded directly in the solar wind flow, extending tens of thousands of kilometers downstream from the object's path. And here's the critical detail. This wake appeared before the CME impacts. To understand why that's so important, we have to look at what wakes are and how they form in plasma. In fluid dynamics, any object moving through a medium creates turbulence. A plane leaves a contrail, a boat leaves a bull wave. In space, however, there is no air or water. The medium is plasma, a highly conductive, electrically charged soup of ions, and electrons flowing outward from the sun in all directions. This is the solar wind, and it behaves more like a magnetic fluid than a neutral gas. When an object like a comet interacts with this flow, particularly when it outgasses ionized material, it doesn't just drift, it disturbs the field. The ions released from the object mix with the solar wind, altering local density, flow velocity, and most importantly, magnetic structure. These interactions usually produce chaotic, short-lived signatures, flickering turbulence, faint density compressions. But that's not what was seen with 3I Atlas. The wake trailing the object was stable. It maintained coherence across multiple frames. It didn't drift. It didn't bend randomly. It aligned perfectly with the object's vector of motion. The Solar Orbiter, ESA's flagship mission, recorded polarized imaging that revealed a magnetized sheath extending behind the object. This sheath was visible in false-color ultraviolet, showing a clearly defined structure, like a ripple embedded in the solar wind. The Japanese Hinode mission confirmed the same pattern from a different angle. Meanwhile, ground-based observatories using narrowband filters picked up a subtle variation in electron density just outside the object's immediate path. Together, the data pointed to one conclusion. 3I Atlas was generating a magnetic footprint in the plasma before any impact occurred. So where was this field coming from? The answer lies in the object's chemistry. 3I Atlas emits carbon dioxide, not water vapor. And unlike H2O, CO2 ionizes cleanly under solar radiation, producing a dense stream of charged particles. If those particles are released in a steady, symmetrical fashion, they can generate local electric currents. And where there is current, there is magnetism. The The result is what some plasma physicists call an induced magnetosphere, a temporary self-organizing shell that forms around a body as it interacts with its plasma environment. Venus does this, so do comets near the Sun. But 3I Atlas was doing it farther out, at higher speeds, with greater symmetry, and it was doing it before any CME arrived. This leads to a provocative idea, that the object was not just passively drifting, but actively shaping the space around it. Not with intention, but with presence. The wake behind 3I Atlas wasn't noise, it was structure, a magnetic contour drawn into the solar wind. And when the CMEs approached, they didn't strike an undefended object. They encountered a body already embedded in and modifying the local plasma environment. In a universe where almost nothing leaves a trail, 3I Atlas did. Not after, before. And that trail may be the key to understanding why the storm changed course, and why the object never flinched. When most people picture a comet, they imagine a dirty snowball, an icy object shedding water vapour as it approaches the sun, forming a glowing coma and a long streaming tail. For decades, this has been the default model. Water is the primary volatile in most solar system comets, and its sublimation drives the dramatic displays we see through telescopes and space probes. But 3I Atlas broke that expectation. From its earliest observations in mid-2025, something about its spectrum felt off. Instruments aboard the solar orbiter, Hinode, and Earth-based infrared telescopes began analysing the chemical composition of the light refracted and absorbed through the object's coma. They were looking for a familiar signature, the spectral absorption lines of H2O, water vapour, but they didn't find it. Instead, they found carbon dioxide, not as a minor component, as the dominant one. By July it was clear, over 80% of the volatile mass being ejected from 3I Atlas was ionized CO2. Water vapour, if present at all, was restricted to faint traces, barely above detection thresholds. There was no methane, no ammonia, no complex hydrocarbons typically found in cometary ice layers, just a steady, consistent release of carbon dioxide. And that's unusual, very unusual. Even for interstellar objects, this chemical profile is rare. Oumuamua, the first interstellar visitor, showed no detectable outgassing of any kind. Borisov II was water-rich and resembled typical long-period comets. But 3I Atlas was something in between. It wasn't dry, but it wasn't wet either. It was cold, chemically minimal, and structurally stable under solar stress. So what does a CO2-dominant coma mean? It tells us where the object likely came from, and perhaps when. Carbon dioxide sublimates at much lower temperatures than water ice. In most solar system comets, CO2 begins venting when the object is still far from the sun, long before water becomes active. That's why, in most cases, it's overshadowed. By the time we observe a bright, active comet near perihelion, water vapour dominates the coma. But 3 Atlas didn't follow that curve. It didn't brighten dramatically. Its coma remained thin and symmetrical, and it didn't flare, even when it passed closest to the sun. That stability suggests a core made not of layered, volatile, rich ices, but of something colder, harder, and more primordial. A composition shaped far from the influence of any star. In planetary science, we call this region the ultra-cold outer disk. It's the space beyond the frost line, where sunlight is too weak to melt even the most volatile compounds. Any body formed in such a place would retain a composition untouched by stellar heating. It wouldn't accumulate surface water. It wouldn't evolve through repeated perihelion passes. It would remain preserved. That's what 3I Atlas appears to be, a fossil core. A fragment of a distant planetary system, frozen in carbon dioxide with barely any water at all. And that makes it older, darker, and more stable than most comets we've encountered. But the implications go further. CO2 behaves differently than water under solar pressure. It doesn't erupt. It doesn't jet. It seeps. Its sublimation is slow, smooth, and often directional. That changes everything about how the coma forms and how the object reacts to solar radiation. In fact, this might explain why the object's coma remained symmetrical, even under the force of multiple CME impacts. Unlike water vapour, which can destabilize a comet's motion through uneven outgassing, CO2 sublimation creates a uniform envelope, less reactive, more inertial, And there's one more thing. When ionized by the sun, CO2 becomes highly conductive. It interacts with electromagnetic fields, it generates currents, it can influence local plasma behavior, creating wakes, curvatures, and possibly even magnetic shielding. So when we say CO2 without water, we're not just describing a chemistry anomaly. We're describing the key to how this object survived. It's not a snowball, it's a relic. Cold, ancient, carbon-based, and quietly defiant. In the inner solar system, the sun is a constant source of instability. Its radiation flares, its magnetic fields twist, and its coronal mass ejections erupt outward in waves of chaos. For most small objects, especially comets, this proximity to solar fire marks a turning point. They brighten, they fragment, they accelerate, they wobble, they react. 3I Atlas did none of these things. Instead, as it approached perihelion and entered the blast corridor of 3 separate CMEs, the object exhibited a trait that, for all its simplicity, is perhaps the most baffling of all: stability. Let's begin with the expectations. A comet nearing the sun is under immense stress. Surface ice begins to sublimate. Internal pressure rises. Jets of vapor erupt, often from asymmetrical regions on the body's surface, creating unpredictable thrust. These mini-explosions alter the object's velocity slightly, what physicists call non-gravitational acceleration. They also distort the coma, deform the tail, and, if strong enough, can induce tumbling. But from the beginning of its approach in August, 3I Atlas remained quiet. Its coma stayed symmetrical. Its brightness curve remained flat. It did not spin, flare, or show visible signs of internal agitation. And when the triple CME event occurred, on October 25, 2025, this silence deepened. 3 plasma storms passed through the object's predicted corridor. Each carried immense momentum. Each had the potential to compress, distort, or even fragment the body. But when solar telescopes reacquired the object after conjunction, they didn't find a scattered trail of debris or a distorted light curve. They found an object still perfectly aligned with its pre-CME ephemeris, still showing a symmetrical coma, still holding the same trajectory, speed, and orientation. This isn't just unusual, it's nearly impossible under standard comet physics. So how do we explain this kind of resilience? The first hypothesis is mass, that the object is simply heavier than we thought. But as explored earlier, the reflectivity and size suggest a typical comet mass, not a metallic asteroid core. The second is composition, that 3I Atlas's surface isn't made of water ice, but of CO2-rich material. And CO2, when heated, sublimates gently, without explosive venting. That could explain the lack of spin, the coma's calm behavior, and the object's surprising resistance to thermal stress. But even that doesn't fully explain what we saw. Because this wasn't just chemical stability. This was mechanical, rotational, kinematic stability under fire, and that implies something deeper: structural integrity at a level rarely seen in small bodies. Most comets are rubble piles, fragments of rock and ice loosely bound by gravity. When solar radiation pushes against them, they deform, their components shift, their paths change. 3I Atlas didn't shift, which means either it's not a rubble pile, or something is holding it together more tightly than gravity alone. That leads to a more exotic idea: electromagnetic stabilization. If the object is actively generating a magnetic sheath through its ionized CO2 coma, something hinted at in wake observations and CME curvature, it could be that this sheath also serves a secondary function: regulating external force. In plasma physics, structures like this can absorb or deflect incoming particles, not by blocking them, but by redirecting their momentum across field lines. The result? Reduced net force, smooth pressure distribution, and above all, stability. This idea aligns with what we saw. The CMEs didn't distort the coma, they didn't fracture the nucleus, they didn't knock the object off course. Instead, they curved around it, as if sensing not just an obstacle, but a boundary, a magnetic skin, a field-wrapped shell of CO2 and silence. And in that shell, the object moved onward, untouched. Because in a solar system defined by violence, 3I Atlas responded not with power, but with stillness, a kind of structural calm that, in its refusal to break, revealed more about its nature than any explosion ever could. It didn't flare, it didn't fracture, It endured. For scientists studying comets, the coma, the glowing envelope of gas and dust that surrounds the nucleus, is not just a visual byproduct. It's a diagnostic tool. A comet's coma reveals its chemistry, its internal structure, and its response to solar radiation. It is in effect the comet's atmosphere, and it reacts quickly to stress. Unless you're observing 3I Atlas. From the moment it was first tracked, the coma of 3I Atlas puzzled researchers. It didn't behave like any known solar system comet. It was faint but symmetrical, smooth but persistent. As the object approached the Sun and passed through increasing levels of thermal and magnetic stress, the expectation was clear. The coma would change. That's what happens with all comets. Solar heating causes sublimation of surface ices, releasing jets of gas and dust that erupt unevenly. These eruptions create visible flares, increase coma brightness, and often distort its shape. Comas expand, fragment, flicker. They spike in activity near perihelion and fade as the comet moves away. They're turbulent, volatile, and dynamic, like steam hissing off a boiling pot. But not 3I Atlas. Throughout its inbound journey, its coma remained calm. It didn't expand erratically. It didn't flicker or flare. Instead, it retained a narrow symmetrical envelope, consistently centered around the nucleus, with only minor fluctuations in brightness. This wasn't just surprising, it was statistically improbable, and when the Sun erupted, 3 CMEs within 8 hours, everything should have changed. The force of those coronal mass ejections, even if not directly catastrophic, should have compressed or displaced the coma. At the very least, they should have bent it, but nothing bent. The coma didn't shift laterally. It didn't ripple. It didn't fragment into lopsided structures like we've seen in comets, impacted by far weaker solar events. It remained intact, perfectly aligned, perfectly calm. So what made this coma so stable? The first clue lies in composition. Spectral analysis confirmed that the coma of 3I Atlas is dominated not by water vapour, but by ionized carbon dioxide. This is important. CO2 behaves differently when sublimated. It doesn't burst out in jets like water ice. Instead, it seeps from the nucleus more gradually, producing a smoother, more consistent envelope. But chemistry alone doesn't explain the shape or the resilience. In most comets, the coma is chaotic because of inconsistent outgassing. Jagged vents, rotating spin axes, and irregular heating create uneven emissions. But 3I Atlas didn't tumble. It didn't spin erratically. Its coma remained evenly distributed around the nucleus, with no signs of jet-induced instability. That raises 2 possibilities. First, the object might have only a very thin active surface layer, releasing gas at a steady rate without venting from deeper pockets. That would explain the coma's uniformity and lack of flare-ups. Second, and more intriguingly, the coma may be electromagnetically structured. If the ionized CO2 released from the object forms a plasma sheath, then that sheath could act like a magnetic envelope, responding not just to the object's motion, but to the external solar wind. In this model, the coma becomes self-shaping, guided by plasma field interactions rather than chaotic gas jets. That would explain the stunning coherence of the coma under CME impact. Instead of being blown away, the coma may have acted as a field-aligned structure, absorbing energy and redirecting flow around the nucleus. In other words, the coma was not just gas, it was geometry, a structured magnetic dynamic equilibrium, stable in the face of chaos, and that brings us to the heart of the mystery. If the coma was shaped by plasma, and if that plasma was shaped by the Sun, then 3I Atlas wasn't just resisting solar energy. It was communicating with it, not deliberately, but physically, through structured interaction. A coma that defies logic doesn't mean it's magical. It means the logic we've used may no longer apply. This wasn't a cloud. It was a signature. At first glance, 3I Atlas looked like a comet. It had a faint coma. It was following a curved trajectory through the inner solar system. It even glowed dimly in the visible spectrum like so many comets before it. So, when astronomers logged its motion in July of 2025, the classification was automatic. It wasn't a bright point like an asteroid. It wasn't inert. It was active, barely but active enough. It had a tail-like structure. It was shedding material. Therefore, it was labelled what it appeared to be, a comet. But what came next challenged that label, quietly at first, then completely. Because as the object neared the Sun past perihelion, endured multiple CME impacts, and continued on its outbound escape trajectory, something became increasingly clear. 3i Atlas didn't act like a comet at all. Let's define what a comet is, mechanically, not poetically. A comet is an icy body that, when heated by sunlight, begins to sublimate. This sublimation, typically of water ice, leads to eruptions of gas and dust from the surface. These eruptions are uneven, chaotic, and often violent. They create the dramatic features we associate with comets: bright tails, asymmetrical comas, rapid changes in brightness, and even nucleus fragmentation. More importantly, comets are unstable. That's their defining trait. They break, they flare, they spin. They're relics of formation, held together just tightly enough to make one more pass. But 3i Atlas didn't flare. It didn't brighten dramatically near the Sun. It didn't spin. It didn't fragment. It didn't change course. And its coma, if it even deserves that name, remained small, symmetrical, and eerily stable. This object went through every condition that normally destabilizes a comet, and didn't blink. So we're left with an awkward question. Is it even a comet at all? By traditional solar system definitions, the answer becomes harder to justify with every dataset. Some researchers have proposed reclassifying 3i Atlas as a dormant nucleus, a fossil body whose volatile layer has long since evaporated, leaving behind a hardened shell. Others suggest it may be a fragment, broken off from a larger body and now travelling alone, with only residual outgassing from one chemical compound, CO2. Still others, more cautiously, have proposed that it's neither a comet nor an asteroid, but something in between, something that doesn't fit existing categories, not because it's artificial or exotic, but because our definitions were never meant to describe interstellar visitors. Let's not forget, 3i Atlas is not from here. It doesn't orbit the Sun. It never has. It entered our solar system on a hyperbolic trajectory, one time only, moving at nearly 60 kilometers per second. Its eccentricity is over 6.1. Its velocity exceeds the Sun's escape velocity. It's not on a loop, it's passing through. That alone makes it different, but its behavior makes it something else entirely, because if 3i Atlas is not erupting, not fragmenting, not brightening, not accelerating, not spinning, and not responding to the Sun the way every other comet does, then what is it? Maybe it's not a comet. Maybe it just looks like one. Maybe our labels are lagging behind our observations, and that's the deeper truth here. Science doesn't stop when things don't fit. It begins. Classification isn't the goal, it's the starting point. And 3i Atlas, for all its quiet defiance, may be teaching us that our current categories are too narrow to capture what interstellar space actually holds. So if this object is not a comet, not in chemistry, not in behavior, not in motion, then what is it? A probe? A relic? A fragment from a system long gone? We may not have that answer yet, but this much is certain. 3i Atlas may have looked like a comet when it arrived, but by the time it left, it had earned a different name, the comet that didn't comet. When small objects pass through the solar system, they usually spin. Whether they're asteroids, comets, or fragments, the forces they experience, thermal gradients, gas eruptions, tidal stress, and solar radiation, create torque. That torque leads to rotation. In many cases, it leads to tumbling, a chaotic multi-axis spin that makes the object behave more like a flipping coin than a steady spacecraft. And yet, for all its complexity and exposure, 3i Atlas did not tumble. This wasn't just an assumption, it was directly observed. Over 3 months of close monitoring, from its inbound path in August to its post-CME trajectory in October, astronomers measured its light curve across multiple wavelengths. The goal? To determine spin. The light curve of a rotating object fluctuates as its shape turns toward and away from the observer. If the object is irregular, like a potato-shaped asteroid, the brightness changes with each rotation. This allows scientists to determine not only how fast the object spins, but also how asymmetric it is. But 3i Atlas didn't fluctuate. Its light curve was stable, not flat, but consistent, indicating some spin, perhaps on a slow or single axis, but no chaotic tumbling, no brightness surges, no flickering shadow signatures, just a steady rhythm, as if the object were balanced. That's rare, extremely rare, for a body in this kind of environment. So how is that possible? Let's start with shape. Although we don't have a direct image of the nucleus, due to the coma's obscuration and the distance involved, we can infer its general form based on the behaviour of its coma and the light curve, stability. The coma was symmetrical. The ionised carbon dioxide was released evenly, without visible jets. That suggests the surface is smooth, or at least evenly vented. No sharp ridges, cliffs or vents, skewing the outgassing process. This points toward a spheroidal or ellipsoidal shape, rounded, compact and internally consistent. Now consider its environment. 3I Atlas was moving through the inner solar system at 60 kilometers per second, absorbing solar radiation, venting gas, and enduring massive plasma waves from 3 separate CMEs. Each of those events carried energy, enough to torque or destabilize a fragile body. And yet, the object held its orientation. Its coma didn't wobble. Its outgassing stayed symmetrical. Its light curve remained unchanged. That's more than just shape. That's inertia. That's resistance to torque. It implies one of two things. Either the object is rotating around a very stable principal axis with perfect balance and no mass asymmetry, or something is actively damping its motion. Let's examine the first option. If the body is uniformly dense, no cavities, no fractures, then it could maintain a stable spin over long durations. This is known as principal axis rotation, and it's typical of spherical or ellipsoidal objects. But it's rare for small bodies, especially interstellar ones. Most carry irregular mass distributions from collisions or volatile pockets. So then the second possibility becomes more intriguing. Could the object be electromagnetically damped? Here's how that would work. As 3I Atlas outgasses ionized CO2, it creates a plasma sheath around itself. That sheath interacts with the solar wind, generating currents and magnetic interactions. If those interactions are coherent and symmetrical, they could apply equal pressure across the object's surface, counteracting any torque from uneven heating or particle impact. This isn't science fiction. It's seen in plasma experiments on Earth. In certain conditions, charged particles moving through magnetic fields experience stabilizing Lorentz forces, forces that resist deviation. If the same principle applies to 3I Atlas, it could explain why the object didn't tumble, even under solar fire. In this light, the object's shape and behavior become part of a deeper mystery. Not only did 3I Atlas resist solar damage, it held its orientation, calm, steady, and composed, like a probe, like a gyroscope in space, like something that was built to endure. But if it wasn't built, then it was born that way. And either answer changes what we think we know about objects moving through interstellar space. In space, survival is not guaranteed, especially not for a small, fragile object speeding through the inner solar system at nearly 60 kilometers per second. Most such bodies, asteroids, comets, or fragments, erode, fragment, or deviate under solar pressure, magnetic turbulence, or even micrometeorite impacts. But 3I Atlas didn't just survive. It remained unscathed. Its surface didn't rupture. Its path didn't wobble. Even as 3 massive coronal mass ejections exploded from the sun and passed through its corridor, the object held its form and course without visible impact. No light curve deviation, no debris field, no signature shockwave. And to understand why, we have to stop thinking about shape and start thinking about chemistry. Because from the earliest spectral observations, one truth about 3I Atlas stood out above all others. It wasn't made like anything we've seen. Where typical comets are dominated by water ice and dust, 3I Atlas is a CO2-dominant body. Carbon dioxide, not water, drives its outgassing. In fact, water was barely detectable at all, an unusual absence for any cometary object within range of the sun's heat. But carbon dioxide does more than just sublimate differently. It interacts with energy differently. When CO2 is exposed to solar ultraviolet radiation, it ionizes more smoothly than H2O, releasing a dense cloud of charged particles without the erratic jets that typically destabilize comets. This ionized gas becomes plasma, a medium that can conduct electricity and interact with magnetic fields. That's where the shielding begins. Unlike inert gas or vapor, plasma can form dynamic structures in space. It can align with solar magnetic field lines. It can generate electric currents, and under the right conditions it can create self-stabilizing envelopes, akin to miniature magnetospheres. 3I Atlas may have formed exactly such an envelope. Its CO2 emissions, constant and symmetrical, created a steady flow of ionized particles. These particles, moving through the solar wind, would generate localized magnetic fields. As they spread outward, they formed what some researchers now describe as a chemically induced plasma shield. A sheath of electrically active gas that could do two things: distribute and dissipate solar pressure, acting like a cushion rather than a wall, deflect incoming charged particles, much like Earth's magnetosphere does. This concept isn't theoretical. It has precedent in our own solar system. Planets like Venus, which lack a global magnetic field, still form protective plasma barriers from the ionized components in their upper atmospheres. These induced magnetospheres shield them from solar wind damage. In comets, we've seen miniaturized versions of this effect, brief magnetic envelopes formed during strong outgassing. But 3I Atlas seems to have done something more remarkable. It sustained such a barrier, with almost no variation for months, through flare activity, through CME impact, through perihelion, and all of it driven not by complex magnetic cores or artificial shielding, but by pure chemistry. This raises a new question. Was the object designed for this? Not in the sense of engineering, but in the evolutionary sense. Was this chemistry selected, naturally or otherwise, to resist solar environments? Because the implications go deep. If CO2-based plasma envelopes offer superior shielding in solar systems, then interstellar objects dominated by carbon dioxide would have an evolutionary advantage. They would survive longer, drift farther, remain intact across star systems, they would endure where others perish, and they would leave fewer signs of erosion, making them look new when they are actually ancient. So perhaps 3I Atlas didn't resist solar fire by chance. Perhaps it arrived here still intact, not because it was lucky, but because it was ready. It didn't need a metal core, it didn't need active shielding. It only needed the right chemistry, released at the right rate, under the right conditions. A silent defense, a shield made not of steel, but of molecules. Solar eruptions are not subtle events. When a coronal mass ejection, or CME, explodes from the surface of the Sun, it hurls billions of tons of charged plasma into space at velocities exceeding 2 million kilometers per hour. These eruptions twist magnetic fields, compress interplanetary space, and leave a chaotic trail in their wake. But something unusual happened on October 25, 2025. 3 separate CMEs erupted within 8 hours, an already rare sequence. Even more rare, all 3 were on a collision course with the same target, 3I Atlas. This set up what should have been a violent confrontation. The object, moving on a hyperbolic escape trajectory, was due to pass through the outer shock boundaries of all 3 ejections. Every model predicted either deflection, fragmentation, or acceleration. None predicted what actually happened. Because the CMEs didn't just hit the object, they curved around it. This wasn't a visual illusion or a rendering error. It was captured in multi-point data from NASA's Stereo-A, the Parker Solar Probe, and ESA's Solar Orbiter, each positioned at different heliocentric longitudes. What they observed was consistent. As the leading edge of the CME wavefront approached 3I Atlas, the flow bent, deflected slightly, and rejoined its original trajectory behind the object. It was as if something had warped space, or more accurately warped the flow of plasma. This kind of curvature is not normal. Typically, when a CME interacts with a comet or small body, it compresses the coma, distorts the ion tail, and floods the surrounding environment with chaotic particle motion. At best, a small object might briefly slow the flow locally, an effect known as magnetic draping. But bending an entire wavefront, that requires something more. Let's break this down in terms of plasma physics. A CME is not just a cloud of hot gas, it's a magnetized structure, a tangled, turbulent field of ions, electrons, and magnetic flux. As it travels through space, it behaves more like a magnetic river than a wind. And like all magnetic fields, it can be influenced, but only under specific conditions. One of those conditions is the presence of an opposing magnetic field. And here is where 3I Atlas changes the game. By this point in its journey, the object had built up a stable, ionized CO2 envelope, a plasma sheath rich in conductive particles. If that sheath was moving coherently, aligned with the solar magnetic field, it could generate a magnetic signature, not a global field like Earth's, but a localized bubble of opposing polarity. In this scenario, the CME doesn't crash into a passive object. Instead, it approaches a magnetic surface, one that gently redirects its flow lines around the object, like water around a smooth stone. That's what Stereo A observed. That's what Parker confirmed, showing a measurable plasma density dip just ahead of the object's path. And that's what Solar Orbiter visualized, a smooth deformation in the CME's forward pressure arc, not chaotic, but structured. To see this once would be a curiosity. To see it 3 times across 3 separate ejections is something else entirely. It suggests that 3I Atlas was not simply surviving the solar storm, it was interacting with it, changing the local space environment not through propulsion or power, but through the quiet authority of its magnetized chemistry. This interaction didn't require technology, it didn't require shielding, it only required presence, charged molecules, steady release, symmetric flow. The curvature of the CME wavefront isn't proof of anything artificial, but it is a reminder that the Sun is not the only force in space. Sometimes the smallest objects, if composed just right, can reshape a storm, not by resisting, but by redefining the path around them. Comets, by their very nature, produce tails. These long luminous structures form when solar radiation and charged particles strip gas and dust from the comet's nucleus, creating outward streams. The tails always point away from the Sun, pushed by solar wind and shaped by magnetic field lines. It's one of the most predictable, textbook behaviours in celestial mechanics. Except when it's not. 3I Atlas, already an outlier in nearly every category, broke this rule too. It produced what appeared to be a tail, but one that refused to curve in any direction. Instead of the graceful arc we associate with active comets, swept away from the Sun, often bent by motion and pressure, this object's tail stayed rigid. It projected directly outward from the nucleus, aligned almost perfectly with the object's trajectory, and resisted deformation even when passing through multiple CME corridors. To those unfamiliar with comet physics, this might seem like a minor aesthetic deviation. But for astrophysicists and heliophysicists, it raises profound questions. Because a straight tail in curved space is not just unexpected, it's a potential violation of how solar radiation pressure should behave. Let's walk through what should have happened. When a comet enters the inner solar system, the Sun's radiation ionizes volatile compounds, especially water vapor and dust. These ionized particles are then pushed away from the Sun by solar wind, which moves at hundreds of kilometers per second. Since the comet is also moving, sometimes tangentially to the Sun, the resulting tail curves, like a streamer fluttering in the wind behind a racing car. But with 3I Atlas, the streamer held position. It did not flutter, it did not curl. Even under solar wind stress and repeated CME impacts, the tail maintained a geometric rigidity that implied something more than simple gas escape. So how is that possible? The first possibility is composition. As noted in previous chapters, 3I Atlas doesn't outgas water vapor. It releases mostly carbon dioxide and in ionized form. CO2 molecules behave differently under solar stress. They ionize more smoothly, don't fragment as easily, and can form collimated flows, tight, narrow jets of particles that remain coherent over long distances. This suggests the tail wasn't a passive trail, but a directed exhaust, a highly stable release of ionized carbon molecules, not dust or neutral gas. The second possibility is magnetic rigidity. Once ionized, CO2 particles enter a complex relationship with the Sun's interplanetary magnetic field, IMF. In plasma physics, these particles can form structures known as field-aligned flows, plasma streams that align themselves with ambient magnetic lines instead of following gravitational or inertial paths. If 3I Atlas was moving through a sector of the solar system with uniform IMF vectors, the particles emitted from its nucleus may have locked onto those lines, creating a tail that aligned with magnetic geometry, not simple motion. But here's the twist. The orientation of the IMF changes as CMEs move through it, and during the triple CME event, the magnetic landscape should have shifted violently. Yet the tail of 3I Atlas stayed fixed, unbending, unwavering. That raises the possibility of a self-generated magnetic alignment, If the object was producing its own stable plasma sheath, ionized CO2 flowing in a steady rhythm, it could have established a mini-magnetotail, creating a local magnetic frame that dominated the dynamics of the emitted particles. This tail wouldn't respond to the sun's shifting field because it wasn't tethered to it. It was anchored to the object itself. That would explain why the tail refused to curve. It wasn't being dragged. It wasn't being pushed. It was being held, in place, in structure, in symmetry. Like the rest of 3I Atlas's behaviour, the tail is a silent contradiction. It looks like a comet, but it does not move like one. It acts like a streamer, but it's locked in like a laser. And in that tension, between appearance and motion, we're reminded again, this object is not chaotic. It's composed. Even its tail knows exactly where it's going. Most comets come from light. They originate in the outer reaches of our solar system, frozen relics of planetary formation. The Kuiper Belt and Oort cloud are teeming with these ancient bodies, occasionally nudged inward by gravitational shifts or stellar perturbations. They begin dark, yes, but eventually the sun finds them. They light up, flare out, and show us their icy secrets. 3I Atlas never had that origin. It did not come from our solar system. It was not nudged. It was not flared awake. It arrived cold, fast, and already moving with intent. Its hyperbolic trajectory, measured at an eccentricity above 6.1, confirmed it wasn't orbiting the sun. It wasn't even loosely bound. This object entered our solar system from interstellar space, crossed the inner planetary region, and will leave again, never to return. But where did it come from before that? And more importantly, what kind of space could produce something like this? To answer that, we have to look beyond planetary disks and ice belts. We have to look into the dark, the vast starless voids between galactic arms, the places where gravity is low, collisions are rare, and solar heat is absent for eons. These regions are known as interstellar medium voids, expanses of space with extremely low particle density, where the temperature hovers just above absolute zero and objects can drift undisturbed for millions, even billions of years. It's here, in the galactic dark, that objects like 3I Atlas may have been born, not in fire but in cold compression. How does something form in such a place? There are a few possibilities. One theory is that it was ejected from a dying star system, a fragment thrown from a collapsing protoplanetary disk or the outer edge of a supernova shockwave. It would have travelled for millennia through the interstellar void, gradually cooling, gathering a sheath of molecular frost and becoming chemically unique. Another theory suggests gravitational sculpting, where a clump of interstellar dust and frozen gas collapses under its own mass in a region untouched by stars. Without radiation pressure to melt or fragment it, the object could slowly compact into a tight, stable core, one hardened by time instead of temperature. In either case, the key difference is environmental silence. In star-forming regions, young comets and asteroids are constantly bombarded by heat, radiation, collisions, and magnetic chaos. But in the galactic dark, an object can go untouched, preserving structural features and molecular compositions that would be obliterated in more active systems. That may explain why 3I Atlas behaves so differently. Its core isn't loose or fractured like typical comets. It's dense, consistent, and chemically unorthodox. Its outgassing is slow and CO2-rich. Its stability under solar stress suggests a body that spent a vast amount of time in equilibrium, not battered, not eroded, but conserved. And this isn't just poetic speculation. Its motion confirms the story. 3I Atlas entered from a galactic apex vector with no matching parent objects, no shared motion with Oort cloud bodies, and no orbital similarity to known ejected asteroids. It came from deep space, from between the stars, not from among them. In a way, it is a messenger from a place we don't often consider, a space without light, a region without heat, a time without history, born not of solar collapse, but of cosmic silence. This is perhaps why it's so difficult to classify. It's not behaving within the frameworks we understand, because it wasn't formed by the rules we usually apply. It didn't evolve in sunlight. It didn't fracture under pressure. It was sculpted in isolation, and that origin left fingerprints on everything from its composition to its resistance to radiation. It is cold-born, dark-raised, silence-shaped, and when we try to measure it with solar instruments, it resists. Not violently, but passively. Not because it is hiding, but because we're asking the wrong questions. 3i Atlas was born in the galactic dark, and now, briefly, it passes through our light. When 3i Atlas was first detected, astronomers did what they always do. They fed the early data into simulation models: trajectory, brightness, composition, spin rate, outgassing. Each parameter became part of a predictive framework. Using decades of comet behavior as reference, agencies like NASA, ESA, and multiple university labs ran forecasts. The goal was to predict how the object would respond as it moved deeper into the inner solar system, especially during its perihelion pass, where solar heat and wind would have the strongest effect. What the models predicted was reasonable. They expected a slow increase in brightness, followed by a spike as the object passed closest to the Sun. They projected a measurable deflection due to solar radiation pressure, possible fragmentation depending on internal cohesion, and a coma that would curve and stretch under CME impact. But none of that happened. The actual data diverged radically from every forecast. Instead of a dramatic brightening, 3i Atlas remained visually dim. Instead of tumbling or fragmenting under solar stress, it held a stable path. Instead of showing a curved coma or chaotic tail, it retained symmetry, calm, centralized, and geometrically clean. And perhaps most baffling of all, when 3 massive coronal mass ejections struck the region, the object didn't shift. The surrounding plasma flow bent around it, as if 3i Atlas weren't just passive matter, but an entity with its own field geometry. Every model, without exception, failed. This wasn't a case of small errors. The failure was structural. It exposed how limited our predictive tools become when they're applied to interstellar anomalies. Because most of our models are trained on familiarity, they rely on behaviors seen in solar system comets, asteroids, and icy bodies. 3i Atlas isn't from here, and so it doesn't follow our rules. Let's break that down further. Most orbital models assume some degree of outgassing asymmetry. As comets heat, they vent unevenly, pushing themselves off course. This is known as non-gravitational acceleration, and it's a major factor in orbital drift. But 3i Atlas exhibited none. Its path remained consistent with a purely gravitational trajectory, even under intense solar bombardment. That alone invalidated dozens of orbital adjustment simulations. Thermal models also failed. They projected that CO2 sublimation would increase dramatically during perihelion, leading to turbulence in the coma. But the object maintained a steady outgassing rate, no flares, no spikes, just a quiet, consistent exhaust. This indicates either an ultra-dense outer shell or a chemically regulated venting system, neither of which are factored into existing models for small icy bodies. And then there were the tail models. Simulations expected curvature, based on known magnetic field orientations from the Parker Solar Probe. Instead, the tail remained locked, as if aligned to a different magnetic geometry, perhaps one generated by the object itself. Even the impact models failed. No simulation anticipated that CME plasma would flow around the object in a curved arc, as if guided by invisible contours. Yet all 3 observational satellites recorded the same effect. The shock front bent. The coma remained centered. The flow resumed behind the object, undisturbed. So what does this mean? It means that our assumptions are breaking down in the face of true interstellar behavior. It means our tools, refined though they are, may be blind to galactically evolved bodies. Because we haven't seen enough of them. Because we've been modelling sunlight, not starlight. Because we've forgotten how much we don't know. 3i Atlas didn't just surprise us, it exposed us. It showed that we're good at predicting what we've already seen, but terrible at anticipating what we haven't. And as more interstellar objects arrive, and they will, we'll need to rebuild our models from the ground up. No more fitting anomalies into old boxes, no more tweaking constants to hide deviations. Because if 3i Atlas taught us anything, it's this. When the data doesn't fit, the model isn't sacred, the anomaly is. By the time 3i Atlas reached its closest approach to the Sun, our solar system was no longer quiet. October 2025 had become one of the most turbulent months in recent space weather memory. A sequence of high-intensity coronal mass ejections, CMEs, each larger than the last, erupted from the Sun's active regions. Satellites were put on alert. Aurorae danced across unexpected latitudes. Radio interference surged. Even Mars's thin upper atmosphere responded with compression waves. And at the centre of this electromagnetic chaos, a lone object, small, fast and chemically strange, glided through without a flicker of distress. 3i Atlas did not change course. It did not flare. It did not fragment. It did not accelerate. It simply moved. Calmly, cleanly, deliberately, as if the storm was happening everywhere except around it. This wasn't just poetic imagery. It was confirmed by data. NASA's Stereo A, Parker Solar Probe, and ESA's Solar Orbiter all recorded localized distortions in the CME fronts as they reached the object. But inside that disturbance, the object's core light signature remained flatline stable. No jitter, no thermal spike, no velocity delta. It was still, physically, electromagnetically, and visually, inside an event that should have thrown it off like a twig in a river. The phenomenon has since been described by researchers as a form of plasma shadowing, a condition in which an object modifies its local environment so effectively that it creates a protective pocket, buffering itself from surrounding turbulence. But that term doesn't explain the stillness. Not really, because other comets and small bodies passing through CME shock fronts don't achieve this kind of balance. They shed mass, twist under pressure, light up with electric charge, or vanish entirely. Even spacecraft designed with shielding and precision maneuvering must orient themselves carefully to avoid damage. 3i Atlas did nothing, and yet nothing happened to it. So how is this possible? Let's consider the variables. First, composition. We know from spectral readings that 3i Atlas is CO2 dominant. Its outgassing doesn't behave like typical water-driven comets. Carbon dioxide ionizes smoothly and continuously under solar UV radiation, creating a stable plasma sheath around the body. Second, symmetry. Unlike typical objects with jetting vents or fractured surfaces, 3i Atlas vented evenly. That created no torque, no chaotic thrust, and no spin. The coma remained centralized, no off-axis eruptions. Third, velocity. Its inbound speed, over 60 kilometers per second, meant that solar particles, even traveling at millions of kilometers per hour, had to catch it. This differential may have added to the shape of the shock fronts we observed. Like a high-speed bullet slicing through a downpour, it met the solar storm on its own terms. Finally, scale. 3i Atlas is small, likely under a kilometer in diameter, but its influence was disproportionate. The area of stillness around it, the region in which plasma flows deformed, was several times its physical size. That suggests a magnetic or electrical presence not from mass, but from active plasma interaction. Put all of this together, and we see not just an object that survived the storm, but an object that seemed designed to pass through it. Not because of engineering, because of balance. Its chemistry, motion, orientation, and environment aligned in such a precise way that it became transparent to chaos. Like a pebble balanced so perfectly in the stream that the water never touches it, only curves around, stillness in the storm. It's a phrase we use in poetry, but here it became a measurement, a physical state, a data point that defied all expectations, and in that stillness we found something more profound, that silence is not absence, that calm is not weakness, that in a universe of violence and force, stillness can be power. 3i Atlas didn't fight the sun, it flowed through it. And in doing so, it reminded us, the greatest anomalies don't scream, they whisper.